So in the model of the atom, we have protons and neutrons in the center forming the nucleus, and then we have electrons flying around the outside. Typically in chemistry, what we're concerned with is if, say, we have another atom and they might share electrons, or maybe one will completely steal the other's electrons, and they form bonds. But in nuclear chemistry, what we're concerned with is the change of these subatomic particles in the nucleus. So particles can leave, particles can come in, or particles that are inside could change. So that's what we're going to be concerned with in this video. So some quick notation. Whenever we're referring to nucleons, we're referring to these. Nucleons. We're referring to the subatomic particles that are in the nucleus, so just protons and neutrons. Recall our mass number is the number of protons plus neutrons, and then the atomic number is just our number of protons. And when we're doing nuclear chemistry, the way we're going to write elements is like this. We're going to put our elements, so say we have carbon, and this is carbon because it has 6 protons. We're going to put mass number on top and then atomic number on bottom. So that is carbon 12. And what we're going to be comparing here a lot is the stability of the nucleuses. So when we're dealing with chemical reactions, they change because different formations and configurations of the electrons can vary in stability. It's the same thing with nuclear reactions in that the nucleuses of the atoms can vary in stability. So for example, carbon-12 is a very stable atom because this isotope of carbon exists in 99%. So another carbon that exists is carbon-13. It still has 6 protons, which is what makes it carbon, but it has 7 neutrons instead, which gives it a mass number of 13. And it's significantly less stable. This one exists in about 99%, and this one's about 1%. So that's what we're going to be comparing a lot. And these are called isotopes. When you have the same number of protons, different neutrons, that's an isotope. So another isotope could be chlorine-35 and chlorine-37. So this one I believe is about 75% and 25%. So once again, mass number on top, atomic number on bottom. This one has 18 neutrons, just 35 minus 17, and this one has 20 neutrons, 37 minus 17. So protons on the bottom, and then the top is the mass number, which is neutrons plus protons. We also can write nuclear reactions in this sense. Similar to how we write and balance chemical reactions, we can also balance nuclear reactions. So we can balance these top numbers as an individual reaction. Say this is X. I could do 232 equals X plus 4. So then what would that X be? Well, obviously X has to equal 228. So then 228 is the mass number of my radium, or whatever Ra is. I don't even know. And then same thing for the bottom. We could do 90 equals 88 plus 2. So we can do nuclear reactions and balance them in a similar way as chemical reactions. Let's get into the exam problems. So for the first one, which of the following atoms have a different number of neutrons? So we know our top number is the mass number, and the bottom number is our atomic number, which is protons. So if we want to find out the number of neutrons in each one of these elements, we can subtract the mass number from the atomic number. So mass number, which is the top, equals protons plus neutrons, and atomic number, which is the bottom, equals just protons. So if we take mass number and we minus the atomic number, we get neutrons. So you just got to take the top number and minus the bottom number. 103 minus 45 gives me 58. Let's go on to the next one. 104 minus 46. This one also has 58. 105 minus 47. This one also has 58. 104 minus 44. This one has 60 neutrons. So this one has a different number of neutrons. But let's just check the last one just because. 106 minus 48. 58. So D is the correct answer here. And we're good. Okay. Next one. Identify the proper isotope and element X represented in the nuclear fission reaction shown below. So here we just have to balance the reaction. We can set up an equation for the top line as well as an equation for the bottom line. So 235 plus 1 equals A plus 143 plus 3 times 1. Or, oops, that's just 3. So if we just solve this, 236 minus 146, A equals 90. And then if we do the next row, 92 plus 0 equals Z plus 56 plus 3 times 0. 3 times 0 is just 0. And then Z equals 92 minus 56, which is 36. So Z is our atomic number, and 36, if we look at our periodic table, corresponds to krypton. How fun. Okay, so we have 90 and 36 krypton, which looks like A. So we can have particles coming in or out of our nucleus. And what do some of these look like? Well, we can have 3 types. The first type is a alpha particle, which has 2 protons and 2 neutrons. So we write it like this. Obviously, the 2 protons and 2 neutrons give us a mass number of 4. And equivalently, obviously, 2 protons is equivalent to a helium atom. And this can lead to alpha decay. So as I showed earlier, you can balance reactions, and you can essentially just put this in to figure out what you get. So say we had chlorine 35, and I want to find out what happens after it goes through alpha decay. So I know it's emitting this particle, so now if we just balance it, I'm going to get 31, and I'm going to get 15. And the element that corresponds to 15 protons is phosphorus. So that's an alpha particle, an alpha decay. And let me move this out of the way a little bit. We're going to need all the room. Beta particles, we can have positrons, which is 0, 1 beta, or electrons, a 0, negative 1 beta. And beta decay exists in 3 different forms. So let me draw this line. We can have beta decay, where we lose an electron, and in our nucleus, this is going to turn one of our neutrons into a proton, which I'll show you. So say again, let's take the same example, chlorine 35, and we're emitting a electron. If we balance this now, we know we're going to get 18 and 35, which is argon. Comparing the chlorine 35 to argon 35, we can see that the mass number stayed the same. So the neutrons stayed the same, but the atomic number increased by 1. So we just converted a neutron into a proton. We can also have positron emission. And this is going to turn a proton into a neutron. If we do the same deal, chlorine 35, and now we have a positron that will convert one of our protons then into a neutron. So, and the 16th element is sulfur. Okay, and then we can also have an electron capture into our nucleus. And this is going to turn a proton into into a neutron. And if we do the reaction for chlorine-35 again, we're going to have our beta particle on the left-hand side of the equation because it's coming into the nucleus. That was supposed to be a beta. Oops. And if we balance this, it's 16 and 35. Now notice the product for these two are the same. So a positron emission and an electron capture into the nucleus actually function the same. And we'll see that here in a second. Let me make this just a tad smaller so we can see gamma. Okay. A gamma particle is just a photon. So it has a 0 mass number, 0 atomic number. And this just happens in excited atoms and they lose a photon. So, for example, if I have chlorine-35, I'm going to have chlorine-35 after. Oops. But I could have emitted a gamma particle. That one doesn't change our nucleus at all. Okay, so those are the types of particles we can emit and some of the ways we emit them. So now, when are these going to occur? We know nuclear reactions happen to make our nucleuses of our atoms more stable. But what's more stable, and when are these different ones going to occur? So that's when we can look at the stability band. So if we just look at our atoms and which ones are more abundant, take carbon, for example, a very common element. We know carbon-12 is about 99% abundant. And nitrogen-14 is also very abundant. I don't know the number for this one. But if we look over here at these most common elements, we can see that their atomic masses are almost perfectly double their atomic numbers, which means they almost entirely exist in the isotope of 1 proton to 1 neutron. So we would theorize that these 1-to-1 ratios of neutrons to protons are really stable. So if we plotted protons versus neutrons, we might expect a perfect 1-to-1 line. But if we observe the rest of the elements, we can see that the fit starts off 1-to-1, but actually increases like this. So if we look down here at some of these heavier elements, we can see that the atomic mass is over double the atomic number, which means they have more neutrons than protons, which describes this fit. So we can see as our protons increases, you're going to need more neutrons to stabilize it. So for example, for whatever W is, say it's at 74 protons, and it has an atomic mass of about 184. I don't know why I need to calculate that. That means it has a rough neutrons of about 110. So it needs more neutrons to stabilize its protons. Which leads us, now that we have a band for how to predict where stability is, we know all the isotopes of elements that exist in nature stably are somewhere along this curve or near this curve. Oops. Let me just erase this. So this gives us a good means to predict what's stable. And not only what's stable, but what type of decay we're going to undergo. So if we're in this region, let me get a color. If we're in this region, it means we have too many neutrons for our number of protons. So if we remember from before, what's going to convert a neutron into a proton? Beta decay, or emission of an electron. So if we're in anywhere up in this region, we know we're going to undergo beta decay. If we're somewhere down in this region, we have too many protons for our neutrons, and our nucleus is going to undergo positron emission, or we could do electron capture. So those, whether either side of the stability band we're on, we know we're going to approach that line. If we are too heavy, any element that has greater than 83 protons is going to, which means we're up in this, anywhere up in this region, we're going to approach the line from the top left using alpha decay. Because we're too big. We have too many protons, and it's an unstable nucleus just because we have too many protons, and we're going to approach that line. Okay. So this is a good means to predict which type of decay you're going to undergo, or nuclear reaction. Let's do some quick examples of this just to illustrate what I mean. So let's just pick an element at random. Say we have silicon, which is atomic number 14, and let's say we have 50 for our mass number. That means we have 14 protons, and we have 50 minus 14 neutrons, which is 36. So if we were to plot this, let's say 14 might be there, and 36, I don't know, somewhere right there. So we'd be up in this region. And we know now that we have too many neutrons, so we're going to approach this line with beta decay. So if a problem were to give me silicon 50, I know it's going to undergo beta decay. It just has too many neutrons. Let's do the same thing. Let's say we had, clean this up. Let's stick with silicon, say, which is 14, say I had silicon 20, and we're still at 14 protons. Now I know I have 6 neutrons, which might only be here. Now I'm right there in my region, and now I know I'm going to undergo beta emission, or positron emission, or electron capture to approach that line. Let's say now we know for alpha decay, it's anything with greater than 83 protons. So if we look at our periodic table, that is any element starting right here. We have this whole row and this whole row. So let's say we have, where is it? I think U is uranium. We're at uranium, which is 92, and it has a 238 for its mass number. So we're at 92 protons, 146 neutrons. It's like somewhere up here. We're up in this region, and we're too big, so we're just going to undergo that alpha decay to approach the line. So that's kind of some examples of if they give you a problem, giving you an element like this, you can predict what kind of nuclear reaction it's going to undergo. Okay, next problem. The sand dunes of the southern Kerala coast in India are endowed with several minerals, including monazite, which includes neodymium. What type of decay would a 160 mass number, 60 atomic number neodymium nuclide undergo? Wow, I definitely butchered a lot of names there. Also included in this problem is the band of stability. Here's what the actual plot looks like. This is the one-to-one line I was talking about that's predicted, and then how it actually curves up over time as the heavier elements require more, the heavier elements up here require more neutrons to stable their protons. Okay, so let's just plot this and see where it lands. So we have, we know neutrons is just 160 minus 60, so 100. So we got 60 protons, and 100 neutrons. We're right there. And we know we're going to approach that band of stability, and that is beta decay. Oh, okay. So if we just look at our answer choices here, beta decay. And if we think about this logically too for another second, if we do it more than just applying our relationships, being up in this region means we have too many neutrons. And beta decay, we know, converts neutrons into protons, which will lead us to that line. So E. The transmutation of 238U into 239NP happens through which series of decay processes? Okay, so the first thing we can observe is that we're adding one mass number and we're also adding one atomic number. So we're essentially just adding a proton into our nucleus. But this is in 2 steps. So let's just go by process of elimination. So if I'm looking at A, we're going to capture a neutron, and let's write this out too, actually. So neutron capture, which would be 1, 0, N, and this would give me 239, 92, and then followed by alpha emission. That would give me 42 alpha and then 235 and 90. So then this would be my final product. According to what A says, this would be my final product, which it's definitely not. So not A. And let's see. I'm going to keep, so this arrow is the neutron capture, right? So I'm going to keep that because the next one also uses that. Followed by, so we have the neutron capture, and then that's followed by proton emission. Okay. And we know that's 0, 1. Or not proton emission, positron emission. Okay. Which gives us then 239 and 91. And once again, this does not correspond to that. So, no. Electron capture followed by beta emission. Let's check this one. This one shares a different first step, so I'm going to rewrite it. Wait, I was doing the same thing. Okay. Electron capture, so that is 0, -1, beta particle. If we balance this, 238 and 91, and then beta emission. Oops. So you're capturing an electron and then emitting it right away, so you get the same final answer. Interesting. So then this, and that does not correspond to that once again. So it's not C. Okay, neutron, let's go back. I'm going to erase this. Let's go back up here. We have our neutron capture and then beta emission. So if we have our beta particle and we balance it, 239 on top and then 93, which does match that choice. So looks like we're going to go with D, and let's check the final answer. Well, and the final answer is just gamma, and we know that's 0, 0. So that leaves us with 239 and then 92. So it's not E, D. Okay, now let's get into some more of the math problems. So there's 2 main types of the math problems that you're going to see. The first one is going to be the half-life, which essentially just requires the use of 2 formulas. The first one being that the reaction rate, that looks really bad. Okay. The reaction rate equals the natural log of 2 over whatever the specified half-life is, and that also the negative reaction rate times T equals the natural log of our final amount divided by our initial amount. And you can use these two equations to pretty much solve for anything. We know we have two equations that we're going to use, and we're just going to work through those. So what do they tell us? We have we want to know what percentage of carbon-14 remains in the wood of a bristlecone pine that is that many years old, and we know the half-life. Okay. So when we read what percentage remains, that is this quantity. So let's solve for that quantity. N over N naught. And N is how much material you have at the end divided by how much you have at the beginning. So that's essentially my ratio of how much of the original carbon's left. And that equals E to the negative KT. And I also know the half-life of carbon, which is this variable. So we can solve for K. So I'm going to use now this equation. This is 1. This is 2. K equals the natural log of 2 over 5.73 times 10 to the third. Let's figure out that reaction rate. (1.21 times 10 to the negative fourth). So that's now my K. And we want a percentage. So I'm going to times each side by 100. And then we have negative K. And we also know T, so I'll just write these in. We're plugging that value, and then our T, which is 4 times 10 to the third. Okay. Put this in our calculator. So I got 61.64, which is percent, which is C. We know mass and energy are related through this relationship, E equals mc squared. And what this implies is that if we have a reaction that changes in energy, we're going to have a resulting change in mass as well. So when we've looked at chemical reactions in the past, there are energy changes that have been associated with them. So there is actually a mass change from products or from reactants to products potentially. But the energy changes associated with chemical reactions and through breaking and forming electrical bonds is really small. So we've always neglected the change in mass that has been associated with them. But as I'm sure you can imagine, with nuclear reactions, the changes in energies are way bigger. And the resulting change in mass is not going to be as negligible. So it's worth studying. So let's take, for instance, these two boxes here. On the left, it's the same number of nucleons and electrons in each case. And each one of these, if I calculated on the left, if I added up the mass of all the protons, all the neutrons, all the electrons, I would get some mass. And then experimentally, I can find out the mass of the nucleus and of the atom on the right. And even though they have the exact same number of electrons, protons, and neutrons in each case, these two masses are not the same. They're actually different by something called the mass defect. And this mass, when we form a nucleus, this one is always going to have lower mass than when we just calculate the mass of the particles floating in space. And we can actually use this in relation then with delta E equals mc squared to get the binding energy for nucleuses. And it can tell us a bunch of other information. So one example of a problem you might see is, what's the binding energy of iron 56, say? And I could calculate this mass using the mass of a proton, the mass of a neutron. I could take my number of protons, times it by, the mass of a proton, whatever that is. Add up my number of neutrons times the mass of a neutron. And then that would give me this mass. And then this mass would be told to me probably in the problem statement, or if it's a one isotope, if it's an atom that has only one common isotope, it would probably be the AMU that's on the periodic table. But they'll probably tell you that in the problem statement. That's something that's experimentally found. So I'll just call it X. And these are probably going to be in AMUs, also associated with these problems. A little aside, there's going to be a ton of unit conversions. So we usually measure the mass of atoms in AMUs. But for the sake of this equation, we're going to want SI units, so we're going to have to convert into kilograms. So you're going to take this mass, subtract off the mass that they probably tell you, and this should be a positive number, because when we form a nucleus, this nucleus and this atom is always going to have a lower mass. So this number should always be positive. And then we can take our delta M and plug it into this equation. And then you're going to use C, which C is the speed of light, which is always a given. That's a constant. That's never going to change. And then you're going to get some delta E. And then your delta E is going to be in joules per nucleus. So if we were to solve this, we would get a delta E, which would be in joules per one nucleus. And a lot of times, just an aside, the questions are going to ask you per nucleon. So then you could take this delta E, divide it by number of nucleons, which would just be protons plus neutrons, and then you could get joules per nucleon. And you could also convert that into electron volts. This number in these units is going to be really small. A lot of times these are worked with in electron volts, but that's how you can solve for the binding energy of a nucleon. Let's also take a look at fission and fusion. So first of all, before we get into this graph, what are fission and fusion? Fission is when we have a big element that's going to split into two smaller atoms. And fusion is the opposite, when we're forming one big atom. So this is fusion, fission. And it's kind of has the, as the name implies, fusion, fusing together. I don't know. And they do this to form more stable atoms and compositions. So we can take a look at this graph up here. We're plotting mass number versus binding energy per nucleon. We want the highest binding energy per nucleon. So when we're at the absolute peak up here, these are the most stable. So as we go further down into, say, uranium-238 or uranium-235, these are unstable. And since they're bigger, they're going to undergo fusion to go in this direction. Same with the elements on the left-hand side, the small elements, they're going to fuse together to move up to that point. So they're going to form and converge through fusion or fission, depending on which side they're on, to get to this middle point right here, which is the most stable. So you want high binding energy. And as they undergo this process, in both fission and fusion, you're going to release a ton of energy. And we know that energy is related to mass through that relationship. And as you release energy, you are losing energy. And so your mass of your nucleons is going to decrease. So this will show up in some problems that we can see later. But that's an important point, is that the mass of your system per nucleon per se, up here would be lower than it would, say, on the right. So, important aside, also common applications of this, generally nuclear reactors, and with those you're going to use uranium-235. This is just a little aside. I know this shows up in a problem, but the fuel is usually uranium-235. And this is a common example of a fission reaction. Okay, let's look at some problems now. 14. The mass of a gold-197 atom is that AMU. What is the nuclear binding energy of a gold-197 nucleus in units of joules per nucleon? So as I mentioned earlier, we know that delta E is going to be related to delta E, or delta M C squared. And we are looking for this delta E, and we're going to have to solve for that delta M, and then C squared is just a constant, and there might be a couple unit conversions we have to do, which I threw over here on the left. So let's first get delta M. We're going to need to do the mass of all the particles added up minus the experimental actual value they give us. So I'm going to call that the mass of the particles minus the mass of the atom, the actual value. So how do we get mass of the particles? And that's going to be delta M. So the mass of the particles will be my number of protons times mass of a proton, which is this value, or that value. And then we're going to add the number of neutrons times mass of neutrons. You could also do the electrons, but electrons have insignificant mass compared to the nucleons. So I'm going to ignore them. Perhaps if we're off by 0.1%, that might be why. But I digress. Okay, so then we're going to get, for this problem, the mass of the particles is equal to, okay, we need to actually figure out how many protons and neutrons. So when we look at gold on the periodic table, we can see that it is atomic number 79, which means it is 79 protons. And if we are gold 197, we are 197 minus 79. That was my mass number minus atomic number, which gives me 118 neutrons. So now let's just start plugging stuff in. 79 times the mass of a proton. It's an AMUs. Plus 118 times mass of a neutron. I'm pulling this from the left. This probably, well, not probably, this will definitely be given to you if you need it on a test. I would hope. Okay. So then, if we do that math, we get that the mass of the particles is equal to 198.641. Okay, and then let's find our mass defect. So now I'm gonna, let's see, I'm just gonna go, yeah, we'll do this. We'll do, mass of the particles is 100, oh, that's big. Oops. Mass of the particles is 198.641 AMU. Forgot to write it, this is also AMU. And they tell us that the mass of a gold 197 atom in the problem is 196.966. Wow, that's a lot of decimals. AMU. So then if we subtract those two numbers, we're going to get 1.674 AMU. Okay, so now we have the delta M. When we plug into this equation, though, we are going to want to put stuff in SI units so that we get joules. So let's make AMUs into kilograms. So I'm going to go over to the left now. 1.674 AMU. And in 1 AMU, there is 1.66054 times 10 to the negative 27 kilograms. It's right here. if we do that. Put that in our calculator. We're going to get that. Let's see, our delta M is equal to 2.7799 times 10 to the negative 27. Okay, so there's our delta M, and we should be good now to just plug this into the equation. So delta E equals, and this is kilograms, 2.7799 times 10 to the negative 23 kilograms times the speed of light, which is 2.99792 times 10 to the 8th meters per second. That's squared. So let's put that in our calculator. And I get, did I do that right? Yeah, it looks right. Okay. And then since we kept everything in SI units, we are going to get this in joules per nucleus. So this, this is 2.498 times 10 to the negative 10, and that is joules per nucleus. Because we did this whole calculation on the basis of the entire nucleus, and we know that in one, we're out of space, in one nucleus of this gold atom, let's put that on the top. Our conversion here is going to be in one nucleus. We have, how many nucleons do we have? 197. We have 197 nucleons. So then nucleus cancels, and then we get joules per nucleon. The reason I did the last conversion is just because I know that's what the answer is looking for. They want joules per nucleon. So we're going to take that answer, divide it by 197, and let me write this up in red at the top. I got 1.268 times 10 to the negative 12, and that's joules per nucleon, which is D. Okay, I moved part of my mess upwards, so it's less messy now. Problem 31. The mass of a helium atom with a mass number 3 is A, the same as a hydrogen atom with mass number 3, slightly less than that of 2 hydrogen atoms and 1 neutron, more than that of 2 hydrogen atoms and 1 neutron, or equal to that of 2 hydrogen atoms and 1 neutron. So let's see. A helium atom has, it's going to have 2 protons in the center, and then since it has a mass number 3, 3 minus 2, it's got 1 neutron. So that's the nucleus of a helium atom. And let's just see off the bat if there's any difference between these answer choices. So a hydrogen 3 atom has just 1 proton and 2 neutrons. So right off the bat, answer choice A does not seem likely because the mass of a proton is not the same as the mass of a neutron. Also, the graph on the right, if we look at it in a second, is probably going to be consistent with the fact that the mass isn't the same. And then let's see, B, C, and D all reference the 2 hydrogen atoms and 1 neutron. So let's see, a hydrogen atom is just a proton, and they're kind of separate like this. So I guess these bottom 3 choices are proposing it's the same amount of nucleons, 2 protons, 1 neutron, as this atom, as the helium-3, but they're not binded together in one nucleus. And we know that when you do bind together atoms to form a nucleus, you lower the mass, always. So this one has a lower mass than all 3 of these choices, which would leave us with B. Okay, so intuitively, without even looking at the graph, actually, we can kind of come to B. No, maybe we don't even need the graph. if we also look at the graph, though, for that answer choice A, we can also see, yeah, that hydrogen-3 is a little bit higher up on the graph than helium-3. So they would have a different mass, because we know mass decreases as you move that way on the binding energy per mass number graph. 32. Which of the following statements is true? When a heavy element undergoes fission, there are fewer nucleons after the reaction before. There's less mass in the same number of nucleons. There's more mass in the same number of nucleons. Or there is more nucleons after the reaction than before. So we know for sure. Oh, and I attached down here, we have an example of a fission reaction. And we know, let's just take a look at the mass numbers. That is still balanced. So the idea that there are more or fewer nucleons is definitely not true. That is never going to happen even in nuclear reactions. We're not creating or destroying new nucleons. Our reactions still have to be balanced. So A and D are wrong for sure. And then now we just have to figure out, is there less or is there more mass in the same number of nucleons? We know, let's take a look at this graph up here. We know that energy is related to mass in this relationship. And when we undergo fission, and I'm sure this makes a lot of sense, you release a ton of energy. Think about an atomic bomb. That releases a ton of energy. And as you release energy, it's essentially like lowering your energy. So then you're going to have a resulting lowering mass. So in a sense, as you go this direction on the graph, you are going to lower your mass per nucleon. So when you do fission and fusion, there is always going to be less mass in the same number of nucleons for both fission and fusion.